Hello ladies and gentlemen, hope you're sitting down ready to take notes. Today we're going to cover two different concepts. First is very much in the textbook called scientific notation. You'll have come across it before. The second, because we're in a sciencey theme, is something called significant figures. Or for those who are cool, we just call them sig figs. Now, sig figs appear a lot in science, a huge amount in science, and they're used to tell us the precision of a result. We don't really use them in maths because maths is pure, see the cartoon, but they're used a lot in science, in the sciences. So in maths we tend to cover them, and in VCE levels you'll need to know them as well as decimal places. You can all round to 2 or 3 decimal places, I hope. By VCE you'll be expected to answer to significant figures as well. So the question might say answer to 3 significant figures, and that will be different to answering to 3 decimal places. It may be different to answering to 3 decimal places, and I'll explain why. Alright, but first, scientific notation. Scientific notation is a number is written in scientific notation. It is of the form a times 10 to the m. So we're looking for a times 10 to the m, where the a is between 1 and 10. So the absolute value of a is between 1 and 10. So it is less than 10, greater than 1. Note that that means it can be anywhere between positive 1 and positive 10, or negative 10 and negative 1. Now, m is an integer, so this number up here is a whole number. 1, 2, minus 3, 7, no decimals in m. Alright, so converting these to scientific notation, now you've seen this in year 9, so I'm going to go relatively quickly. We want the decimal place to be here, because we couldn't put it there because that would make the number in front of 12. And we want the number in front to be between 1 and 10, so we want to move it to between the 1 and the 2. And if we want to move it between the 1 and 2, we are jumping it 2. Now we're jumping at 2, so it would be 1.2354 times 10 to the power of 2. Note 10 to the power of 2 really is 100. 10 with 2 zeros, sorry, 1 with 2 zeros, 10 to the power of 2 is 100. So we're taking this number here, multiplying it by 100, and that will get us back to here. We haven't changed the number at all, we're just writing it in a different form. Alright, here. We want the decimal place to move to there. The reason we want it to move in between the 4 and the 5 is because that way the first digit will be between 1 and 10, or negative 1, negative 10. Now note the negative sign stays. We're then jumping it 1, 2, 3, 4 places. And we write this as 4.56, so the decimals move between the 4 and 5. In order to move it that way, we multiplied it by 10 to the negative 4. We're jumping it back 4. Right. Note that that's really the same as dividing it by 10,000. So we're taking negative 4.56, dividing by 10,000, and getting back to this number here. Alright. This one here, 1.0.1003. We only need to jump it once. So this would be written as 1.003. Note we keep those 2 space zeros there. They're important. Times 10 to the neg 1. We've jumped it back 1. Converting from scientific notation. So from scientific notation, 10 to the 4 means it's being multiplied by 10,000. Quite a big number. We're going to jump the decimal place 4 zeros. 1, 2, 3, 4. Every time we do a blank jump, you add a 0. So 3, 2, 9, 0, 0. And the decimal place is now there, although you wouldn't write it by convention. You would leave the decimal off and just write it as that. Now, negatives. And we're negative power. Negative power means we're jumping back. So that's 1 jump back, 2, 3, 4, 5. Decimal place is now there, and we're putting in placeholder zeros there. So it will become negative 0. Then 1, 2, 3, 4, 1. Those were the 5 jumps. 5, 6. Same here. Only 1 jump. This direction becomes 10.09. Alright, we will do more practice in class. Now, the more confusing thing is significant figures. Alright, in science, I'm not a science teacher, but almost all of science is based upon measurements. There are very few values in science which are defined. And since all measurements are uncertain, we must only use numbers that are meaningful. A common ruler can't measure something to an accuracy of 22.402643 centimeters. Realistically, you could probably get 22.4 off your ruler. Anything beyond that, you're guessing a bit. Now, only some of these decimals actually have significance. So if your ruler was pretty good, you could go 22.4. Writing the rest of it is meaningless, because you don't know what the rest is. If you were using a laser micrometer or a vernier caliper, by all means you can measure more accurately. But with a common ruler, 22.4 is as accurate as you can get. So therefore, those are the only decimals that have significance. Adding digits after that really doesn't add to the accuracy of your answer. You're just making stuff up. So in science, we use the number of significant figures in an answer to give an indication of how precise our measurements are. Alright, I'll give another example. Say it's 10 kilometers from Hamilton to Tarrington. Now note, 10 kilometers, when just setting conversation, you implicitly assume that really that means anything between 9.5 and 10.4999 kilometers. If the actual distance between Hamilton to Tarrington was 9.6 kilometers, or the actual distance from Hamilton to Tarrington was 10.4 kilometers, you would completely be forgiven for saying in general conversation that it's 10 kilometers. And going by the trip odometer in the car, yeah, about 10 kilometers is fine. So when you say it's 10 kilometers from Hamilton to Tarrington, the level of precision you're assuming really is just this digit here. You just have worried about getting it right to the 10 mark. Now, note, that's very different to saying it's 10.0 kilometers from Hamilton to Tarrington. I realise that both of them say exactly the same thing, 10 and 10.0, in terms of distance, but one implies much more accuracy. This second one here, 10.0, really implies you're going from 9.95 and up to 10.04 and down. You're rounding to this one decimal place there. This number here, by adding the 0.0, you're implying a far greater degree of accuracy. You're saying, I've measured this really quite accurately, it is 10.0. I can go to one decimal place, and this is where we use significant figures. The number of significant figures in each of these is different. This one here would have one significant figure, the 1 being the only significant one. This one here would have 3 significant figures. And the rules to this are confusing. And they're a little vague, so I've tried to make them as simple as possible, and there are some very good articles to read online about it. Alright, clearly, if someone said it was 9,765.42 meters from Hamilton to Tarrington, they are saying it's 10 kilometers, about, but they're saying far more than that. They're saying they've measured it to the nearest centimeter. I'd be calling them a liar, but using that number of decimal places implies I know it down to the nearest centimeter. Or they know it down to the nearest centimeter. Alright, there are 3 rules for determining how many significant figures are in a number. Non-zero digits are always significant. So if you count the number of non-zero digits, there are at least that many significant figures in it. Any zeros between 2 significant digits are significant. So for example, if you had 906, these are significant from the first rule. This is significant from the second rule. There would be 3 significant figures. Any trailing zeros in the decimal portion only are significant. That's where people really get confused. To carry this example a step further, 900 has trailing zeros behind it, but they're not in the decimal portion, therefore they're not significant. So the number of significant figures in this is just 1. Going to our examples above, here, this is a trailing zero in the decimal portion, therefore it is significant. The 1 is significant from the first rule. Now note, because the 1 is significant and the trailing zero in the decimal is significant, the 1 here, because it's trapped between 2 significant figures, is also significant. So telling 10.0 has 3 significant figures uses all the rules. It uses the fact non-zero is significant, the 1, trailing zeros are significant in decimals, that's the final 0. The middle one is significant because it's between two significant figures. Alright, so, confusing. And there's a fantastic article on that link. Do read it. There's a fable there. A fable is like a fairy tale with a point. Read that as well. It's good fun. I'm sorry this video has gone for so long. Then, on OneNote, have a shot at these. Identify the number of significant figures. After you've had a shot at them, and I won't waste your time by going through them all, there are the solutions here. And the solutions, very helpfully, for the fantastic website above, have explanations of why they're significant. Alright, so for example, you should be able to look at this and say it has 5 significant figures. The reason is because those two are significant because they're numbers. That one's significant because it's jammed between two significant figures. These two are significant because they're trailing zeros. You should be able to look at this one here and say, well, significant, significant, jammed between significant, therefore significant. So 3 significant figures, 5 significant figures for that. This one here, these are not significant. These zeros are not significant because they don't trail. This just has 3 significant figures. That there's a comma, it's bad to see, but the trailing zeros here are not significant. It's a bit like our 10 kilometers, just one significant figure. What's significant is those 3, so it's 3 as well. This one here, those are not significant. The zeros between are, it's 4. Alright? We will do more practice in class, but can you continue those ones and look at explanations if you get stuck? Thank you very much. Stop recording.